long here, and it reads, so it's kind of a fill in the blank first, and then they give us an example to solve. So the fill in the blank reads, to solve a polynomial inequality, we factor the polynomial into irreducible factors and find all the real blank of the polynomial. Then we find the intervals determined by the real blanks and use the test points in each interval to find the sign of the polynomial on that interval. So let the polynomial be p of x equals x times x plus 2 times x minus 1, and fill in the diagram below to find the intervals on which p of x is greater or equal to 0. So what is this really asking us to do? Okay, so first of all, we need to determine what a polynomial identity is, okay? So they gave us the polynomial p of x equals x times x plus 2 times x minus 1. Okay, so the polynomial inequality, like any other inequality, sets this polynomial to be greater than or equal to some kind of number. So in this case, our polynomial inequality reads that this has to be greater or equal to 0. Okay, so we need to find all the values of x that will make this value greater or equal to 0. Okay, so this is going to take us a while, because there could be a lot of different values of x that will make this equation true. So we're going to go work through this systematically, and we're going to have to determine the zeros. And I'll get into why we need to determine the zeros in the first place. Okay, so let's draw a number line here, okay? Actually, let's just draw a positive and negative, okay? So this is our x and y axis, okay? We don't really care about the y too much, but I'm just going to put positive y, negative y, all right, and positive x, negative x, okay? So the zeros of a polynomial are the solutions to the equation when this polynomial is equal to 0, right? So it's the values of x that makes this polynomial equal to 0, okay? So I'm not going to graph it out per se. I'm just going to use a different example. So let's say that we have polynomial of a different polynomial. So it's like f of x, okay? And we know that this is going to be a polynomial, okay? And let's set f of x to be equal to x squared. So we know that this is going to be a parabola. Maybe we should do x squared minus 1. Okay, so we'll set x squared minus 1. So if it's x squared minus 1, then we have this. This is our polynomial right here, okay? So here we have a third degree, but we're going to use a second degree, okay? And I'm going to describe why the zeros are very important in this case. So the zeros help us to determine where the polynomial is equal to 0. So the zeros are here and here, which is positive 1 and negative 1, okay? So these are the only values in the entire polynomial, and the entire function itself, which will equal to 0. And this helps us to find the parts of the polynomial which will be positive, and the parts of the polynomial which will be negative. Because if we are guaranteed that these are the only values that are equal to 0, then the values in between the zeros are going to be negative, and the values outside of that interval is going to be positive only. So you see here on our example here that the values between our zeros of 1 and negative 1 are all negative, right? If there was another 0 here, for example, then it might switch to positive and back to negative, right? But we know for a fact that the values between our zeros are either going to be all negative or all positive. So you see here, past 1, it's positive, and past negative 1, it's positive. So when we're filling in this blank, right? So to solve a polynomial inequality, we factor the polynomial into irreducible factors. So and find all the real roots or zeros of the polynomial. So we're doing what we usually do with a quadratic equation, with a polynomial equation. We find the zeros of our polynomial. And by doing so, we can use these zeros to define intervals in which we can determine whether the polynomial is positive or negative within those intervals. Okay? So let's use the example that the question proposes, okay? And also I'm going to use this diagram that they use, I guess, too. So, so given our polynomial of p of x equals x, x plus 2, and x minus 1, we have 3 zeros here, okay? So I'm going to draw a number line here again. Okay, so this is infinity, and this is negative infinity, okay? So we'll have our first 0 of -2, our second 0 of 0, and our third 0 of 1. Okay, these are not drawn to scale, but we know for a fact that based on our polynomial, which is already factored irreducibly, we have zeros of 0, -2, and 1. Okay, so now we're going to use test points within these intervals that are defined by our zeros to figure out whether our polynomial in this interval here is positive or negative, and whether our a polynomial is positive or negative in this interval and this interval. So we have 4 intervals we need to check. So we have this interval, which is -infinity to -2. We have this interval, which is -2 to 0. We have this interval here, which is 0 to 1. And we have this interval here, which is 1 to infinity. Okay? Cool? Cool. So we're going to gather test points from each of these intervals, and we're going to sub them into our polynomial and see if it comes out negative or positive. Okay? Alright, so let's test out our first interval here, which is -infinity and -2. Okay, let's use our test point of -3. Okay, so if we were to write p of -3, what do we get here? We get -3 times -3 plus 2 and -3 minus 1. Okay, is that right? Is that our polynomial, by the way? Yeah. Okay, so what do we get here? So we get -3 times -5 times -4. So we have negative, 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 -15 times negative. So 15 times -4 is 60. Oh, whoops, 60. So it's -60. Okay, so given our principle that every value in between the intervals of our zeros has to be of a negative value or positive value, we can then conclude that in this interval of -infinity to -2, all the values of our polynomial are negative, given this test point. Okay, let's do our next test point here. Let's do -2 and to 0. Okay. Let's use a test point of -1 because that's in between each. So we have -1 times -1 plus 2 times -1 minus 1. And that gives us -1, 1 minus 2. And that gives us negative times negative times positive is negative times negative is positive, so we get 2. So now we have determined that in between this interval, p of x is greater or equal to 0. In this interval here, we know that p of x is less than 0. Okay, let's move on to our third interval here, which is 0 and 1. Okay, so we'll test out p of 1 over half. So that's 1 over half minus half plus 2 minus half minus 1. Okay, what do we get here? We get 1 over half times 3 over 2 minus 3 over 2. Alright, so this is going to be negative, negative, positive, negative, so it's going to be 1, -1. Yeah. Let me just check my math here. 4, 8, that's not right. That's going to be -9 over 8. Man, my math is bad. Okay, so we know that in this interval here, our polynomial is always going to be negative, so less than 0. And finally, let's test our last interval here, which is 1 and infinity. So we're going to use 2, for example. So p of 2 is equal to 2 minus 2 plus 2. Hold up, sorry. That's 2 plus 2. I don't know why I wrote a half here. this should not be negative there. This is 2 plus 2. And it's going to be 2 minus 1. I don't know why I wrote halves here. That's that's my mistake. I'll change this after I finish this. So it's 2 times 4, 8 times 1, which is 8. Okay, so we know that p of x is greater or equal to 0. Okay, let me just change this for real quick here. So this shouldn't be negative. That shouldn't be negative over there. Okay, so what we get here? This is actually 5 over 2. So this is 5 over 2, and this is going to be negative half. Right? And so that's going to be negative 5 over 8. Sorry about that. I don't know why I wrote negative half there. Okay, so cool. So we've tested all these intervals out, and we've found our solutions. Okay, so let's just write down our final solution here. Therefore, in intervals negative 2 to 0 and 1 to infinity, p of x is greater than 0. Okay, cool. So that's how you solve this this question here. We first of all found the irreducible factors because they were given to us. We found the zeros. We reasoned that the values between the zeros will always be negative or positive. So then with that reasoning in mind, we tested each of these intervals by making a test value and seeing what the value of our polynomial is. And by doing so, we found the intervals that our polynomial is positive or greater than 0. So there are other ways to really do this. You can use derivatives. You can also reason with the nature of polynomials that the intervals and the regions actually interchange. So it goes from negative to positive to negative to positive, and there's zeros. There's a ton of ways to do this. You can even graph it visually and just look at where it is positive. But overall, we use this method of test points and intervals to find our positive values of our polynomial. So this solution is correct. Good work. Cool. All right, let's move on to the next question.